In this lecture, we're going to be graphing derivatives. There'll be practically, I don't think there'll be any computation at all. This will strictly be looking at pictures and trying to determine how to graph the derivative based on the picture. So, let me begin with, I've got a few graphs ready and waiting for us to pick. So, let's start with number 1. Now, what I want to do here is look at the graph and try to determine what the graph of the derivative should be. So what I'm going to do is I'll copy it in. And I really don't need a lot of it for this particular thing. I'm not going to give you the formula. I don't care about that so much as just getting a picture of the derivative. So let's throw that in. And let's take a look at it. You have the graph of a line. Now, according to the derivative, if you pick a point on the graph, the derivative will give you the slope of the tangent line at that particular point. And then, of course, you can go and find the equation of the line at that point. Well, the thing is, the point is on a line. That means the tangent line is actually the same as the line itself. So, if the derivative is the slope of this line, then I need to find the slope of this line. Let's write down what I wanted to do here. Draw a graph of dy over dx, the derivative with respect to x. So I put my point on a good spot, then I'm going to find another good spot, which I see it goes through a corner point here. What is the slope of this line? Well, if I go down 1, 2, 3, 4, 5, let's see, I went down from 8 to 2, that's 6, and then I went over 2, so m equals 6 over 2, well, negative 6. Remember, if you go downward, you count that as negative. Negative 6 over 2, which equals negative 3. So, in fact, I want to graph the line that's simply y equals negative 3. It should be at negative 3, but basically dy over dx equals negative 3. The slope of the tangent line is simply the same as the slope of the line. Now this is cool. Check this out. This graph program allows me to graph the derivative on the same graph as the original one. So let's check and see if I did a good job here. So I'll just go up here to function, insert CF, insert F prime. It's even got the dy over dx. How cute. So there we go. I don't care about the range. I don't really want it in red. I've been told that colors are not such a good thing to use on YouTube, especially for people that can't see them. So we'll stick to black. In fact, let me come back here. Let me make it as thick as the original graph. And you can see right there that that's pretty much the thing I drew. Let's take a look and compare. There it is. Mine was a little bit off because I have to learn to use my stylus a little better, but there you go. Alright, let's grab some more. Really, the idea here is simply to get you comfortable with the derivative and what it does. Let's graph something curvy. So here we have a parabola. So let's grab this. Now this will elucidate much more of what a derivative does. A line really doesn't do much anything for anybody. Alright. Now what we're always interested in is where the graph is increasing or decreasing or is not doing either of them. So what we have to do is look at various places on the graph, and I'll get you comfortable with this in a minute, but as you can see, if I pick my point to be in that spot and I take a look at a potential tangent line, what can you tell me about the slope of that possible tangent line there? The possible slope is negative. M is negative because the line is going downward. So what you have here is the graph of the derivative is below the x-axis. It's negative so long as the original function is decreasing. Now, it keeps doing this, albeit less and less and less of negativity as you go down here. It flattens out and flattens out. So I might do something like this. You can see that the lines are getting less and less negative if you just kind of keep them. It's hard for me to draw these things, especially on this thing. So let's see if I can get one here pretty flat. By the time I get here, though, what you'd call the bottom of the parabola, you'd have to say that that tangent line has got to be flat. What's the slope of a flat line? It's 0. So I will have my graph increase until I get to 0. And so therefore, on the entire way down, the entire decreasing part, this part right here, was all negative. And that corresponds to the graph below it. And it's finally 0 there. Now, if you pick a point over here and draw a tangent line, just nothing fancy, just draw one in, what can you say about the slope of that line? That line has a positive slope. So now the derivative is going to be positive. And you can see it started at 0, but as you went up, it increased the amount of increasing it's doing, I guess you could say. So I'm going to have something like this. So this thing here, that's my dy over dx. So it's all about recognizing where it's positive and negative. These are crude graphs. They're not exacting in nature, but you get a feel for how the function's working. I dare say these might even be fun. All right, let me take this back. Now, I'm going to check ourselves by graphing its derivative and see how close I was. Now, keep in mind, I wanted it to be 2. So let's take a look at mine. Mine was a little curvier, but we both hit at 3.5. You notice there they're 0. The x-intercept for the derivative is 3.5. 3.5 here. But the important thing right now is to note that I'm negative to the left of 3.5 because the function is decreasing there, and I'm positive to the right of 3.5. Those are the important features of the graph of the derivative. Where is it positive, negative, and 0? Let's grab another one. Graph number 3. We got a curvy one this time. More curves. Now I can now that I've shown you what I did, I can give you a way to work these things now. So, draw a graph of dy over dx. Now, what I'm going to do, instead of going positive and negative first, I'm going to look at all the places where I have zeros. Any place where the tangent line is horizontal, like right here. Horizontal tangent line. And I got one over here too. Horizontal tangent line. I'm going to put a 0 there. So I know the graph of the derivative will have to go through those points. Now, how do you do those points? Well, if you look, let's pick something over here that's to the left of that point. So let me fill this point in. Now just draw a crude tangent line. And what do you notice? It's positive. So that'll correspond to having something like this. See that? Now, from this point here to this point over here, the tangent line is going downward. So the graph is going to be in the negative for the derivative. But keep in mind, it's got to hit the 0 between 1.5 and 2, so it's got to come back up. Once it hits it, it goes like this. Because after this particular point, the original function is increasing again. Tangent line has a positive slope. So what it looks like is something like this. So dy over dx, once again, is this guy. Kind of like a parabola. Now let me go to the graph and let's see how we did. So highlight this and then you tell it to graph f prime of x. And you can see we didn't do such a bad job there. If you look, do you see where we have? I have a 0 here, approximately, for the derivative, and my derivative 0 is pretty much the same. They have a 0 here between 1.5 and 2, then it goes up, and it does look like a parabola, doesn't it? Same over here, sort of parabolic, so that's good. I have all the important aspects in there, where it's positive, negative, and 0. We will deal with more refinements, like where there are wiggles in the graph and things like that later. But right now, we just want to feel for these things. Graph another one. Close this guy out. Nope. Let's go on to number 4. Ah, now this is interesting. This has a point in it. What happens at a sharp point? Well, let's take a look at some tangent lines. I'm going to start above negative 4.5, and I'll draw my crude tangent line as normal. As always, my crude tangent line. It has a negative slope. That means my graph will be below. But I'm not going to have a 0 here. Do you see what's going on? If I keep following this graph down, the slopes of the tangent lines are going to get steeper and steeper. In fact, what they're doing, if you look, if I were able to draw tangent lines, they would go like this. But then at negative 3, what they would do is the tangent line at negative 3, since you have the graphs form, I guess, some sort of a V, but it's not quite a V. It meets here. The tangent line right there is an actual vertical line. So you have here a vertical tangent line. So the graph here, in fact, let me get rid of what I did, because the graph that I have so far should never be positive. Not so far. Why? Because it's always decreasing. And you notice it seems to level off maybe as you go farther out and farther out. Maybe it does, maybe it does not. But I do know it does something like this. And it becomes very steep toward that asymptote. Now the other side's very simple too. It's just going to mimic the other side because this graph looks completely symmetric. So when I draw the graph here, this thing down here is dy over dx. Note that dy over dx has a vertical asymptote at x equals negative 3. So the derivative is not defined for that particular number. I'm glad I stopped myself just now. You might be able to tell that I've made an egregious error here, and I hope that I'm going to leave it in because I think it's very useful. You'll notice that the tangent lines to the left of -3. So over here, tangent lines were negative, so the graph is negative. However, if you pick a point over here, these tangent lines are positive. This graph should have never been below the x-axis. Let me grab this stuff, take it out of here. It should have never been below there. Instead, it's positive. As it gets to -3, you can see that it has an extremely vicious positive slope. So really, this piece is going to go like this. And it's going to stay positive the whole time. So it still has the asymptote, like I said, except it's in two pieces. Here, where the negatives were, and then here, where the positives were. So be careful. I tried to use symmetry. In fact, you might, if you look at the original function, it kind of looks like it's symmetric about the line x equals -3. It's sort of like an even function that's been shifted to the left 3 units. Well, its derivative kind of looks like an odd function that has been shifted to the left 3 units, and that's not an accident. You'll see that happens quite a bit. Let me check myself again. This is how I would have found this out at this point anyways, but let's go ahead, graph it, and see what happens. Okay, there's my one piece. I don't know if I can get them both on there at the same time. I'll tell you what, let's move this one up. Give that graph back. Yeah, we can see it now. So follow my mouse pointer, you can see this is the left piece of the graph of the derivative, and it matches sort of the left piece of mine. And then here's the right piece that seems to match mine. Notice that it stays positive the whole time because this function is increasing. To the left of -3, it stays negative the whole time because the original function is decreasing. Okay, let's graph another one. Really, the idea here is just to get you comfortable with all the different things that could possibly happen. Ooh, look at this. Now, let me go to this point. This happens at 3 also. 3 apparently was popular with me on this stuff. I'm going to see how vertical of a line I can draw at 3. Oh, I got to get it in the right spot, don't I? There we go. That's not so bad. Do you see the tangent line is vertical at 3? It's a vertical tangent line at 3. But down here, if you look at tangent lines to the left of that, tangent lines to the left are positive, and tangent lines to the right are also positive. So the tangent lines are always positive, except here it goes to infinity. So this is a case where you're going to see, if it's got to go to infinity when you get to 3, it's going to be positive. It looks like it's smoothing out as I go out to the left. So something like this. Not quite. But the same thing is happening to the right of -3, except -3 is the place where the derivative should be tending to its highest. So it looks like this. See that? So on the left, positive slope. Let me use my mouse for this. To the left, positive slopes of tangent lines corresponds to the derivative being positive. Then, of course, it has an asymptote at x equals -3. Then over here, it is still positive, except it's tapering off because the amount of slope is decreasing as the graph goes on. All right, let's take a look at what the calculator tells us. It's a shame, I think, that we use calculators to determine if we're right or wrong. And there you go. You see, it's almost exactly what I told you. If you look at it, there, let me use my mouse again. There's their left piece, which is similar to my left piece. The right piece is similar to my right piece. So let me write something down here. dy over dx is this piece, and this piece. And then finally, one last thing to consider, and it's an old test, and not that old. It comes from, I think it's 2017, and I'll increase these as needed. This guy right here, number 10, that's exactly what I wanted. See if I can make it the full screen. Okay, good. Let me take this thing and answer the questions that are given. Alrighty. What you have here is the graph of a function f of x is given. At each of the values of x given, specify the value of the derivative, fill in the blanks. So let's start with f of negative 5. Let me go to negative 5. Right here is negative 5. And so I am on, the graph is a straight line there. Let me put the dot. So all I need to do is figure out the slope of that line. Well, if you look, the slope of the line here, it goes down 1 unit, and then it goes to the right 2 units. Since it's down, it's a negative slope. Down 1 unit over 2, or to the right 2, we get negative 1/2. Okay, easy enough. Now the next one, f prime of negative 2. So here's negative 2. Here we are. Here's the graph. Let me put my dot at negative 2. I'll try to make it big enough so you can see where I'm messing around at. Well, this is easy because the graph of this tangent line is horizontal. Horizontal tangent lines have slope 0. Easy enough. Next, f prime of 0. That's down here. So down here, when x is 0, we have what's called a sharp point. Let me show you what happens here. If you look at the derivatives, you're going to have a negative. This derivative will be negative because it's going downwards, decreasing. But then it's followed by one that has slope 0. Well, that means from the left you'll have a negative slope, and from the right you'll have a positive slope. So the derivative's not going to exist because the left and right limits are not the same. So best you can do here is put a dne. Okay, what's next? F prime of 1. This is 1 right here. F prime of 1. Easy enough. This is on a line whose slope is 0. Then finally f prime of 4. Put that here. This is on a line with a positive slope. So all I got to do is figure out the slope of the line. So I'll start here. I'll go to the right 2 units, and then up 1, 2, 3, 4. So it goes up 4 for 2 to the right. So 4 over 2 equals 2. And there you have it. That's, hopefully you'll play these back over and over again. Do them slowly. Try to do them yourself as well, because you're only going to get better. You wouldn't believe some of the stuff that people put for this particular question, but there's no reason for it if you think about what the derivative means. That's exactly what this section is all about. So I'll stop there. I think I've done plenty for today on that particular one.